Imagine a blank piece of graph paper. Two distinct groups of dots suddenly appear scattered across the page, some bright red and some bright blue. If I asked you to separate the red dots from the blue ones, you'd probably just grab a pencil and draw a straight line right down the middle. For a human, doing that is entirely intuitive. But a computer algorithm can't rely on a best guess. It needs a mathematical way to calculate a dividing line that is perfectly balanced between the two groups. That is exactly what a support vector machine, or SVM, does. It is a specific algorithm designed to find that optimal boundary, which data scientists call a hyperplane. SVM focuses on the dots that haven't arrived yet. By locking in a permanent boundary now, the system can automatically sort new data points into the correct group with high confidence. An SVM doesn't just draw a thin line, it expands outward to form a wide road called the margin. It stretches until its edges physically bump into the closest red and blue dots. These dots are support vectors, guarding the road's edges. To the algorithm, the hundreds of other dots fading into the background do not matter at all. Those few border guards dictate the entire setup. If one of them takes a step to the left, the whole road has to shift to accommodate it. Maximizing the road width creates a large buffer zone between the groups. This extra space acts as a safety margin. If a future data point is slightly off-center or messy, it is still likely to land on the correct side of the road. So how does a computer actually steer this road into the perfect position using math? Look at this central dividing line rotating to find its path. The algorithm uses a mechanical dial called weight. Weight acts like a steering wheel, adjusting the exact angle and slope of the line so it can fit cleanly between the clusters. Controlling the angle is half the job. Otherwise, the line is trapped spinning in the dead center. To fix this, the algorithm uses bias. Once the angle locks, bias acts as a sliding mechanism, shifting the line physically away from the center point. By combining the steering angle of the weight with the shifting position of the bias, the SVM can navigate across the graph and drop a perfectly straight divide exactly where it needs to go. This graph shows a much trickier problem. We have a tight central cluster of red dots completely surrounded by a dense ring of blue dots, forming a bullseye. Try to draw a straight line or a wide road through that. On a flat piece of paper, it is physically impossible to separate these two groups without placing a dot on the wrong side. To solve trapped shapes like this, the SVM relies on a mathematical shortcut known as the Kernel trick. The Kernel trick calculates the data in 3D space. Watch the central red dots elevate above the blue ring. The algorithm slots a flat boundary sheet between them. Viewed top-down, this flat cut forms a perfect circular boundary. Whether the SVM is shifting angles on a flat surface or calculating distances in 3 dimensions, it finds a consistent path to separate complex data into clear, reliable categories.